Welcome to part 2 of module 1 of the course Ultrafast Optics and Spectroscopy. In part 1, we have given an introduction to the subject, and in this part, we will continue the discussion on the ultrafast timescales and capturing events in that timescale. Ultrafast spectroscopy is an advanced time resolved spectroscopic technique. A time resolved technique monitors how a system evolves as a function of time. Ultrafast spectroscopy enables us to capture events, mostly microscopic, both physical and chemical, in very rapid time scale. In general, time scale in time resolved measurements may span from hour, minute, second, milliseconds, microsecond, nanosecond, picosecond, femtosecond to attosecond. So, these are the different time scales we are introducing: millisecond, 10 to the power minus 3 second, microsecond, 10 to the power minus 6 second, nanosecond, 10 to the power minus 9 second, picosecond, 10 to the power minus 12 second, femtosecond, 10 to the power minus 15 second, and attosecond, 10 to the power minus 18 second. So, these are the relevant time scales one might be interested in time resolved spectroscopy. However, when we say ultrafast spectroscopy, we in general consider this portion of the time scale: picosecond, femtosecond and attosecond. Modern ultrafast spectroscopy includes time resolved measurements only in picoseconds, femtoseconds and attoseconds time regime. Like any time resolved measurement, if we consider any time resolved measurements, that will include two important measurement elements. The first one is, in any time resolved measurement, we measure time either directly or indirectly, and then we record events in time. So, measuring time, I need a clock. For this, I need a clock, and recording events in time, what I need? I need a time sensitive detector. So, these are the two devices I need for measurement of time and recording events in time, and these are the two elements would be present always in any time resolved spectroscopy, including ultrafast spectroscopy. Our interest in measuring time and recording events in time has a long history, as schematically depicted here. It is first reflected in ancient development of calendars in about 4000 BC. So, we developed calendar long time ago, and calendar was kind of a time measuring device which helped us to understand processes in terms of years and days. Followed by sun clock in about 1500 BC. The sun clock was developed. These early developments permitted us to record yearly and hourly activities, events with the help of our eyes. So, when we have used sun clock or calendar, these are the clocks we have used. So, these are the clock, that is the time measuring device, and to monitor the evolution of the events we have used our eye. That is the time sensitive detector we have used. Time sensitive detector. Then development of mechanical clock in about 1000 AD enabled us to measure events in duration of minutes and seconds. So, we developed this mechanical clock, and that enabled us, gave us second and minutes time resolutions. Before 1800 AD, however, our ability to record the timing of individual events in progress was essentially limited by the response time of human vision, blinking of an eye, approximately 100 milliseconds. As I told you that all these clocks we have used and as a time measuring device, but the detector, time sensitive detector, is eye, and we can use this time sensitive detector as long as the event is slower than the response time of eye. Response time of eye is 100 millisecond. So, any event which is slower than 100 millisecond can be captured with the help of our eye. Recording any event faster than the response time of our eye was beyond our scope at that time. Snapshot photography, in which time sensitive detector is placed in dark and is exposed to time evolving event for a very brief time using a mechanical shutter of a galloping horse done by Muybridge in 1878, was the first attempt to record events without eyes in millisecond domain. So, that was the first photography was discovered in 1878, and the galloping horse picture was recorded with the help of the camera. This first photography was nothing but a snapshot camera. It's more like an SLR camera nowadays. The response time of snapshot photography, however, was limited by mechanical shutter speed, which is a few milliseconds. Anything faster than milliseconds was beyond the scope of capturing using snapshot photography in 1878. So, what does it mean? I have a camera or detector kept inside a dark room, let us say, and I have a shutter which is separating outside and the dark room, and I have to pull the shutter and close the shutter quickly, and I can capture the image on the CCD camera or any time sensitive detector. So, the response time of this kind of snapshot photography depends on how quickly I open the shutter and close the shutter. That was the limitation, and it was millisecond at that time in 1800. Then the fast recording technology was shifted from mechanical to optical, resulting in stroboscopic photography performed by Edgerton for the first time in 1964. He recorded an image of a bullet passing through an apple. This image was recorded with the help of not by this snapshot photography. This was used. This photography was here. Snapshot photography was used, but this was done by stroboscopic photography. Stroboscopic photography and snapshot photography, they are a little different. In stroboscopic photography, what we do, in snapshot photography, what we do, we have camera kept inside the dark, and we are separating this dark room from the outside world with the shutter, and we open the shutter, close the shutter. We expose the camera for a very brief time to the event. But in stroboscopic photography, we keep the event in a dark room, and we keep the event is going on in a dark room. I have camera pan to the event in the dark room, so I cannot see anything, and then I use a flash of light, a very brief flash of light, and I'll be able to capture the event. That is called stroboscopic photography. So, we had to move to stroboscopic photography because the time resolution which was achieved with the help of snapshot photography was millisecond, and with the help of stroboscopic photography we have been able to get microsecond time resolution. This is microsecond, this is millisecond. Stroboscopic photography was performed using a brief flash of light while the event occurred in dark, and photographic camera was kept exposed to the event in dark as well. A schematic illustration of capturing frames of a rapidly rotating dial, which is A. This dial is rotating. This dial is rotating like this way, and if it is rotating very fast, then what happens? Generally, we experience at home all the time when the fan is rotating very fast, we see a blur image. We cannot distinguish each blade. So, if it is rotating very fast, then we get a blur image by our eye, and in that case, event is faster than the response time of the detector. In this case, detector is our eye. So, if the event is faster than the response time of the detector, then I can use the same detector, a slow detector we call it. Generally, we call it then slow detector. A slow detector can be used, but in that case, I have to use stroboscopic photography, where I have to keep the rotating dial in dark. Then I have to use flash of light at a certain interval. So, in this interval, we see a frame, then again dark, then again flash of light. I see the rotating dial, again I see rotating dial, again I see rotating dial, and that's the way we can capture the image. And this stroboscopic photography is at the heart of ultra-fast spectroscopy. So, a bare eye captures only a blur image. Mathematically, it is called time average signal. So, when I capture a blur image with a slow detector, I am just capturing this minus infinity to plus infinity V signal dt. Over the time, I am just integrating the whole signal, and whatever I am seeing is depicted here in frame B. However, if bare eye, a slow detector, is kept exposed to the event in dark, and a flash of light is used at a certain time interval, different frames of the event can be captured, which together represents time evolution dynamics of the rotating dial. This idea depicted in the bottom frames presented here. The discovery of stroboscopic photography helped us realize that if we need to capture events using a slow time sensitive detector, which means the period of the event is faster than the response time of the available time sensitive detector such as human eye, we have to use faster flash of light. So, now the time resolution of this process will depend on how brief the flash of light we can prepare, because if the event is much faster, very fast, then we have to have even faster flash of light. So, the duration of the flash has to be controlled and selected depending on what kind of event we want to monitor. This realization, this stroboscopic photographic idea, this realization has revolutionized the technology of synthesizing faster flash of light. By 1980s, the flash of light with several hundred femtoseconds duration became available, and today flash of light with several tens of attoseconds duration is available. Our interest in capturing events with rapid flash of light at ever increasingly shorter time scale has given birth to the modern ultrafast science and spectroscopy. With this, it is now seemingly important question: how rapid flash of light is required to observe a chemical event? So, let us say in the rotating dial experiment, instead of rotating dial, I have a molecule like AB molecule, and this molecule is vibrating. Let us say this is a stretching mode. This molecule is vibrating just like a breathing mode. AB bond is vibrating like this way. And if this is vibrating, first thing I have to know, if I want to employ stroboscopic photography, then I have to I have to use flash of light even faster than the period of this vibration. So first thing we have to understand is that how rapid flash of light is required to observe a motion, atomic motion or electronic motion in molecule with the help of stroboscopic photography. So we need to know the intrinsic time scale of atomic motion. First we look at the intrinsic time scale of atomic motion. The time scale of chemical reaction is the time scale of atomic motion of a molecule. I can think about A, B, they are coming closer, forming chemical bond. So this is nothing but vibration. So I have to find out how long does it take to extend the bond, stretch the bond like this and then recompress. How long does it take? If I consider 2000 wave number stretching mode, this is can be obtained from IR spectroscopy. A particular stretching mode can have a particular value, the excitation value. So if it is a 2000 wave number stretching mode, then I'll be able to convert this 2000 wave number to its frequency. This is the frequency we get, and once we get the frequency, vibrational period can be obtained with the help of this equation 1 by nu, and this gives me 16 femtosecond. 16 multiplied by 10 to the power minus 15 second. This is second. So 16 femtosecond. So what does it mean? If I take 2000 wave number stretching mode, 2000 wave number stretching mode could be, let's say sometimes it could be C double bond O. This kind of functional group if we have in a molecule, that kind of functional group will be vibrating, and this kind of functional group will vibrate with 16 femtosecond period, which means that it will stretch, recompress, this whole time would be 16 femtosecond. So this is the time scale where the vibration occurs, which means that if I want to monitor this vibration, then I need femtosecond pulses, and these pulses are nothing but flash of light, a sophisticated flash of light. If we look at the vibrational period 16 femtosecond one more time, and if we try to find out what is the speed of atom during the vibration, then we have to assume that the critical distance traveled by atom during dissociation is 4 angstrom. Let's say I will assume that once the two atoms are having 4 angstrom distance, I will call it the molecule, the bond is dissociated, the bond is broken. And if the bond is broken, then I can find out this for this distance, what is the velocity of the atom to dissociate the bond, and we find that it is 50 kilometer per second. Per second it's traveling 50 kilometer to dissociate the bond. This is the typical speed of atom during the vibration, during the molecular dissociation. Then we will look at the typical time scale for the rotation. Let's say I have CH4 molecule, CH4 which is having C, then 3 hydrogens are organized here and 1 CH bond here. So with respect to this CH bond, this 3CH3, this CH3 group can rotate, and if this is rotating, what is the time scale of this rotation? That is exactly what we are trying to find out. So those kind of rotation having energy 4 wave number. If we have 4 wave number, then very easily I'll be able to convert to its frequency, and from frequency I'll be able to get the time period. And the time period for the rotation we get is this is second. Time period we get is 8 picosecond. Which means if I want to find out a molecular rotation like this, and if we want to monitor how it's rotating in a molecule, then I need to have picosecond time scale, picosecond flash of light. Next, we'll look at the intrinsic time scale of the electronic motion In order to estimate intrinsic time scale of electronic motion in atom, we shall use Bohr atomic model. Although this is the simplest atomic model we have, but we can use that to find out or predict what kind of intrinsic time scale of electrons we have in atoms. So, if we consider Bohr atomic model, which we have a nucleus here and we have an electron orbiting the nucleus, and when it's orbiting there are two forces, which is centrifugal force given by mv square by r centrifugal force, which must be equal to its Coulombic electrostatic force 4 pi epsilon naught r square, which means Coulombic electrostatic force is acting along this way and centrifugal force is acting along this way. They must be equal to stabilize this atom, and if they are equal, then I'll be able to get velocity. Just from this equation I'll be able to get this velocity, and from the velocity, if I know the typical hydrogen atom radius, then I'll be able to find out the distance it travels for the one orbit, and from the distance and the velocity I'll be able to get the time, orbit time of 1s electron in hydrogen atom, and that is given by 150 attosecond. 150 attosecond is the orbit time of the 1s electron predicted by Bohr atomic model. So, in order to record intrinsic electronic motion in atoms and molecules, we need flash of light with attosecond temporal duration. Here we must note that not every nuclear process occurs in femtosecond or picosecond time scale, and not every electronic process features attosecond time scale. For an example, chemical reactions which are driven by mass diffusion occurs in microsecond time scale. However, it is quite clear at this point that in order to record a fast chemical event in time using slow detector or using stroboscopic photography, we need even faster flash of light. The introduction of the flash of light to chemistry with microsecond time resolution came near 1950s with the development of flash photolysis by Norris and Porter. With the advances made with lasers, the time resolution improved continuously over the years, reaching picosecond in 1970s, femtosecond in 1980s, and attosecond in 2000. The 1999 Nobel Prize in Chemistry was awarded to Ahmed Zuel for his studies of the transition states of chemical reactions in the femtosecond time domain. So, before we end this module, we will point again to an important issue. If the available time sensitive detector is slow, let's say I have, so for ultrafast spectroscopy, what I need a detector, and we see that this detector is going to be slow because all electronics are the response time of all electronic detectors are actually nanosecond, which is much slower than femtosecond vibrational motion, picosecond rotational motion, or attosecond electronic motions, intrinsic motion. If the available time sensitive detector is slow, we have to follow the approach of stroboscopic photography to capture a fast event. This means that we need to use rapid flash of light. Duration of the flash of light must be shorter than the period of the event to be captured. What is the typical response time of the fastest time sensitive detectors which we have? The response time, all modern time sensitive optical detectors such as photodiode, photomultiplier tube, power meter, CCD camera, all of them measure voltage or current using electronics, and the response time of the fastest electronics is a few nanoseconds, or if it is the best electronics, then I can have several hundred picosecond, that's all. We cannot have femtosecond or attosecond time resolution or picosecond time resolution few picosecond time resolution with the help of electronics. Therefore, all time sensitive detectors are slow detectors when it comes to measuring intrinsic time scale of nuclei and electrons. Therefore, only a flash of light provides a well defined time window for the time resolved measurements with a slow detector. How a slow detector can be used and what kind of interpretation we have, that is all about this course. So, with this we have come to the end of this module. In this module again we have gone over different relevant time scales, and one important concept which we have introduced is that stroboscopic photography is the only answer to the problem we have. The problem is that we have slow detector and we have very fast event. So, in order to observe that, we need flashes of light with duration shorter than the period of the event. We will meet again for the next module.